finish up root finding today, and we're going to finish up with talking about systems of nonlinear equations. So instead of one equation in one unknown, we've got n equations in n unknowns. So we're doing systems. Okay, so here we want to solve, again, f of x equals 0. But here x is a vector and f is a vector. Okay, so x is going to consist of the components x1 to xn. Okay, and f is going to consist of the components f1, right, which depends on all of the different components of x, all the way to fn, which again depends on this entire vector. Okay, so we don't have a simple method like bisection that is just super robust and kind of works really easily like we do with scalar equations. Oh, right, because we can't just think of, I guess, you know, to the right is this above and to the left is this below. Now we're separating things by planes or by hyperplanes, which is a lot more complicated than separating things by a single point, which is what we do in bisection. So what we're going to do is Newton's method here. A lot of the solvers for nonlinear systems are based on Newton's method, well, not all of them. So this comes down to Taylor expansion again, right? We take our system, we say, let's try to approximate it by its linearization, and then once it's a linear system, we can solve it. So if I'm going to focus on just one of these equations. Okay, let's Taylor expand the ith equation. I'm going to first just do it for n equals 2, where it's simple, and then write down the general case. Yeah?
This may be a dumb question, but does the index of the vector of the function have to be the same as the index of the vector for the, like, do they have to be the same dimension?
Do these have to be the same dimension? Yeah, so yeah, typically they will be the same dimension. So n equations in n unknowns. And if you think towards linearizing it, we certainly want n equations in n unknowns when we linearize for that to have a chance at least of being well posed. And now, you can certainly get cases nonlinear equations are more complicated, so n equations in n unknowns doesn't necessarily, you know, uniquely determine a solution always. Just like with a quadratic equation, there could be more than one solution. So there's always cases where you might need extra conditions. But in general, yeah, the n should be the same for both of these. Okay, so if I Taylor expand, what do I know? I know that fi of alpha, if alpha is my root, is equal to 0. Okay, so let's do this for n equals 2. So if I Taylor expand, I get fi at x. Okay, then I need my first derivative terms. So I got to Taylor expand along the x1 direction and along the x2 direction. So I'll get alpha 1 minus x1 times df by dx1 evaluated at x. Okay, I get alpha 2 minus x2 times the derivative with respect to x2. Okay, so this is the linearization, the first order Taylor expansion, and then we'll have error, and the error is going to depend on second derivatives. Okay, and again, we're Taylor expanding in both x1 and x2, so I'm going to get second derivatives with respect to x1, with respect to x2, and then also mixed second derivatives when I do this. Okay, so when I put in my error terms, what do I get? I get the x1 term. Okay, I get my x2 term. Okay, and then I get the mixed term. Okay, d squared by dx1, dx2, and all of this is acting on f, evaluated somewhere. Okay, so this is the special case n equals 2, but we can certainly generalize this very easily, right? These are terms that depend on the gradient of f. These are the different components of the gradient. And then our error terms depend on the different components of the Hessian that stores all these different second derivatives. So if we want to do this more compactly, more generally, we're going to build this entire gradient. Okay, so the gradient of fi consists of all the partial derivatives of fi. Okay, the Hessian, so this is a vector of length n. The Hessian is going to be a matrix that stores all the second derivatives. So this is an n by n matrix, and if we want to know what elements are in, say, the jth row in the kth column, this is just going to be the second derivative with respect to xj and with respect to xk. Okay, so if I rewrite this kind of more compactly in terms of this, just this gradient and this Hessian, what do I get? I get 0 is equal to fi of x plus, now I have alpha minus, what's that? This should be a k, yeah, thank you. Okay, so plus, I have alpha minus x, those components. So that's alpha minus x dotted with the gradient of f. Okay, so alpha minus x times, let me write this the other way because I've written alpha minus x as a column vector. So gradient of fi of x, which I've written as a row vector, times alpha minus x, which is a column vector. Okay, so that's a dot product of those two vectors. Okay, and then plus my error term. Okay, so this is going to be a quadratic, right, in alpha minus x, and it involves this Hessian matrix. So what we're going to have here is alpha minus x transpose times the Hessian times alpha minus x. The Hessian not at x, but at some point c. Okay, now we know for Newton's method, we're going to ignore this error term because we can't compute it exactly. So when we ignore it, we get a linear system. So if we just use the first order approximation, we're going to get 0 is approximately equal to fi of x plus the gradient times alpha minus x. And now we want to try to solve for alpha, right? Alpha is the root. Alpha is the thing that we want. Okay, so we do this for the first component. We do this for the second component. We do this for the nth component. Now, again, I can put that all together and think of this as a matrix vector problem. So let's combine all the equations now. So all of f1, f2 down to fn. Okay, so this gradient, for any particular component, this gradient is a vector. Now what I'm going to do is stack all these gradients. So I'm going to have the gradient of f1, gradient of f2, and I'm going to stack them into a matrix. Okay, so when I do that, I get this, what's called the Jacobian matrix. Okay, so this is gradient of f1 all the way down to gradient of fn. Okay, and now my first order approximation becomes, okay, 0 is approximately equal to, and now again I'm going to stack all of these. So these are each scalar. Now I stack them into a vector. So I get all of the different components of the function that I'm trying to find the root of. Okay, so now here I have the ith row dotted with this vector. Now I want to do this for all the different rows. So that's the same as saying, let's do a matrix vector product. Okay, so again, this is now a system of n equations, right? f1, f2 down to fn. And I have my n unknowns in here, the different components of x. But now it's a linear system. Okay, and a linear system of n equations and n unknowns, we have tools to solve. Okay, so if we try to solve for alpha, what do we get? We get alpha minus x is going to be approximately equal to, if I move this minus f of x to the other side, minus grad f inverse times f of x. Okay, and that means that the root that I'm looking for is approximately equal to x minus this Jacobian inverse times f of x. You don't look like you believe me.
Why is that a linear system if f of x wasn't linear in the first place?
Yeah, why is this a linear system if f of x wasn't linear? Because now we're not solving for x, we're solving for alpha.
Okay.
So if x is known, if x is just some fixed value, then this is a constant vector, this is a constant matrix, and we're trying to solve for alpha. It's f evaluated at x, exactly. Okay, and this is what we use for Newton's method. So it's exactly what we did for scalar equations, where we said, let's treat f as a straight line and find out where it intersects. Now all we've done instead is said, let's treat f as a plane, or as a hyperplane, and figure out where this thing hits 0. Okay, so Newton's method now becomes, right, we take a guess at x, we plug it into here, and that spits out a new guess at what our root should be. So x n plus 1 equals x n minus the Jacobian of my old guess inverse times f of x n. Yes.
In practice, this is a 2 by k. You mentioned about on the case of n equal to 2, but in general, we don't want to actually find the inverse of that Jacobian. We want to try to solve it by
So you're exactly right. You're saying in general, okay, if n equals 2, you can do whatever you want probably. If n equals 1,000,000, which is reasonable, right, for a realistic problem, you don't ever want to compute the inverse of a matrix. So what we're doing is not building this inverse and then multiplying it by this vector. What we're going to do, and I'll write it down in a few minutes, is treat this as a system of linear equations that we have to solve somehow using some available method. And the available method you want to use usually depends on the structure of your problem. So this is actually an important point for big problems. There's no one-size-fits-all method where I say this is the method that you can use for all problems. You need to learn about your problem and what its properties are and what its structure are. But this is a really good starting point for a lot of nonlinear solvers. What's the order of convergence? Someone says 2. Someone's not willing to guess. It is a fixed point method, sure. It's Newton's method. It's the generalization of Newton's method. So 2 is a good guess. Well, let's check. Well, we don't have to guess. We can try to actually check. Okay, so this is, okay, I'm working with vectors now, but the kind of manipulation I'm going to do here is not different than what we did before when we checked order of convergence. Okay, all that matters is instead of just taking the absolute value of the error, we've got to take a norm of the error. So I'm going to do what I have always done. I'm going to say, let's look at the difference. Let's look at our new error. And we're going to try to get this in terms of our old error somehow. Okay, so we know this is, okay, we plug in what Newton's method is, which is written right there. Times f of xn, okay, minus alpha. Which, by the way, this form of Newton's method shouldn't have surprised you, right? It looks like the scalar Newton's method, right? We've got x minus f over f prime, except now we've got to, instead of dividing, we have to interpret it as multiplying by an inverse. So it really does still look like the scalar Newton's method. Yeah?
Sorry, trivial question. Are we going to be using the convention that we use this superscript instead of the subscript indexing because for vectors?
Yeah, so what I've done here, I've used the superscript indexing only because this has multiple components, and I was using a subscript to index the components. So that's common. Again, what matters most is that you're consistent. But yes, that's why I changed to superscript. It's possible I'll slip up and drop down to subscript later, and you're welcome to point that out to me. I'm going to try to be consistent. All right, so we've got to now manipulate this, right? This part here looks like an xn minus alpha, which is great. This doesn't. This is complicated, and we've got to simplify it somehow. And we're going to simplify it the same way we always have basically been simplifying things, is say, let's try to Taylor expand this, right, about alpha, about our actual root, because we kind of know what's happening at our root, and things simplify when we look at what's happening at our root. Right? For example, we know that f of alpha is equal to 0. Okay, so I'm going to Taylor expand. I'm going to hang on to this stuff out in front. And now I'm going to Taylor expand both of these pieces. I want to get everything in terms of alphas. Again, this is not different than how we analyzed Newton's method before for the scalar case. It's just now we've got matrices and vectors to worry about. Okay, so for this part, I'm going to put this in terms of alpha. Okay, and then plus some error. Okay, so the error is going to be on the order of xn minus alpha. Okay, and just a comment, that, as long as this Jacobian is nice, invertible, and everything, I could move this inverse here, and this will still be an order x minus alpha error. Okay, so I have this times f of xn. So f of xn, if I do about alpha, well, that first term is trivial, right? That's just 0. So let's keep going a little farther. Try to get a non-trivial term popping up here. Okay, so I'm going to have Jacobian of f at alpha times x minus alpha. Okay, plus some error. Okay, so all I've done, I've gone into here and I've said let's Taylor expand and find the first non-trivial component, and I've left everything else as error. So I haven't Taylor expanded any farther than I really need to here. Okay, so I've got one non-zero component, so all I'm going to do is multiply these two non-zero components together and then figure out how big is whatever is left over. All right, so I still have my xn minus alpha out here. I'm going to multiply these two components together, so I have grad f alpha inverse times grad f alpha times xn minus alpha. And how big is the leftovers? Yeah.
I'm kind of confused on the way that we're doing it. Is grad f, that's a matrix?
This is a matrix. This is a Jacobian, yeah.
So then how are we like multiplying those?
So you can multiply matrices together, right?
Sure, but one's into the power of negative, so it's like a sum to the power of -1. Are we just ignoring our error term?
So we're not ignoring, let me rewrite this term. Okay, so now I have some function to the -1 power. Okay. And again, this is, as long as this is a nice function, as long as this Jacobian is actually invertible so that the Jacobian inverse makes sense, and as long as it's continuous, then I can further do, you can think like binomial expansion type thing or Taylor expansion type thing. I can further simplify this to, well, let's use this as my leading order term. This is my leftovers, and the error will still be first order. Right, you're just thinking of this inverse as being, I'm taking g of all of this, where g happens to be an inverse, the inverse function here. So g of all of this, I say, well, let's Taylor expand about here. I get g of this plus a first order term that's left over. Okay, so when I do that, I can multiply this out, and now how big is my leftover piece?
That's going to be the inverse right there, right?
What's going to be the inverse?
The third of those two terms. No. On the second line, yes.
Yes.
So
Right, this isn't exact yet, right? Because I've ignored this term and I've ignored this term in the multiplication. So when I add those terms in, how big is the part that I've ignored? In terms of xn minus alpha, how big is it? To the second power, right? So what's going to be left over? I've missed this cross term, xn minus alpha times this. This is another xn minus alpha, so that's quadratic. I've mixed, this term, but that's cubed, so that's smaller, right? So indeed, what's going to be left over is order xn minus alpha squared. Now, can I simplify this? Yeah, I can, right? Because what's here? This is the best thing I could have hoped for with matrix multiplication. I get the identity, exactly. I have a matrix times its inverse. So all of that is the identity, and what do I really have? I have xn minus alpha minus the identity times xn minus alpha, which is something that scales like x minus alpha squared. Right, so this is going to be bounded by some constant times xn minus alpha squared.
Is that a plus in between those two things? Is that an equal? So you have xn minus alpha minus.
This is a plus, yeah, thanks. Okay, so what's the order of convergence that you see here? It looks quadratic. So if we want to check the order of convergence, what do we need to look at? We need to look at the limit as n goes to infinity, right, of now the norm of xn plus 1 minus alpha over the norm of xn minus alpha to some power. And the natural power that's showing up here is a squared. Okay, and what did we find? Well, we found that xn plus 1 minus alpha is basically the same size as this, right? So this is going to be, let's call it less than or equal to. So this new error, we said, looks like it was bounded by some constant times this old error squared. So we'll call it some constant times my old error squared. Right, so this does give me something that is constant. And that is quadratic convergence. Okay, and this constant here, what's it going to depend on? It's going to depend on the Hessian, right? The Hessian at alpha. So I didn't write down explicitly what the error was. We wrote down explicitly the error actually when we derived Newton's method, right? And it involved the Hessian at an unknown point, and that unknown point was converging to alpha. So somewhere in here we've got the Hessian of f, the Hessian of f, and that's what's coming up in this constant. Okay, so we have quadratic convergence as long as what? As long as this matrix is invertible, and as long as the Hessian, right, is well-defined and continuous. So I'll say we have quadratic convergence if Jacobian of f is invertible. Okay, and the Hessian exists and is continuous. Any other questions on this part? Believe the quadratic convergence? Maybe, possibly. And this is something that you could test on some examples too, right? You could say, let's run an example where I know the exact solution, and let's see how quickly the error actually goes down, and check and see if it really does seem to be doing this, right? What's that? You can get lucky. You can certainly get lucky. And that's why we do this analysis too, right? But this will be common in a numerics paper here. I've built a new numerical method. Okay, hopefully I've been able to prove some things about what I expect to happen, how fast I expect it to converge. And now I do some numerical tests, and I try to come up with a range of examples where hopefully I know the exact solution and check and see, am I actually seeing in practice what the theory said I should see? And hopefully you are. Okay, so now if I wanted to actually use Newton's method in practice, and this point was already brought up, I don't want to build the inverse of a matrix, right? That is something that you never, ever, ever do in real life. So we were trying to do this iteration. Okay, but we can't build this inverse matrix. So since we're not going to construct this inverse matrix, what are we going to do? We have to write this as an equivalent linear system. So let's look at this term and see how we can compute this term as a whole, right? Because we never actually need this inverse. We need the product of this inverse with f. So we just need a way of computing that product, essentially. So let's define yn to be this product. Now, the first thing I want to do is get rid of this inverse matrix, right? So the way to do that is to multiply by the Jacobian, left multiply by the Jacobian on both sides. So this is the same as saying the Jacobian of f times y is equal to f. Right? So again, xn was our last guess, so we know, so we can compute f, and this is a vector. We can compute this Jacobian, and this is a matrix. The only thing we don't know, and the thing that we really want, is this y. So this is a linear system for y. So we need to solve a linear system for y. Right, and that you do with your favorite linear solver. Again, maybe you use some information about your problem. Is there some structure to the matrix that can help you out? So here's our process. Okay, so for each iteration, we compute this Jacobian matrix. Okay, we solve this linear system. Okay, using your favorite linear solver. And for the homework problems where you have to do this, you don't have to build your own linear solver. You can use whatever solvers are available, MATLAB / or whatever is available in the language that you're choosing to work with. Okay, so we solve for yn, and then we say, okay, yn was this product. So now when we do our update, xn plus 1 is going to be our old xn, and then minus this new update that we've computed. Process looks okay? You can code that up? Hopefully. We'll find out. right? But it's the same process as the scalar Newton's method, except we're in scalar Newton's method where we could just do division. Division is the same as inverting a matrix, basically, and that is the same as doing this linear solve. So what are the challenges of using Newton's method? What are some that you see? Yeah.
We have to compute more partial derivatives.
You have to compute a lot of partial derivatives. Yeah, you have to compute this Jacobian matrix, and this Jacobian matrix could be massive. Say I said we have a system of 1 million equations and a million unknowns. That means the Jacobian is a 1 million by 1 million matrix that you have to potentially build and work with, and that is not cheap. So we need to actually construct this Jacobian. Even just constructing this Jacobian and storing this Jacobian can turn into a memory issue before you've even done anything with it. So that's an issue. What else? Sam? What if it's not invertible? If this Jacobian is not invertible? Then we've got a problem, right? And okay, when we were doing scalar Newton's method, we compute f prime and we say, are you equal to 0? Oh, that's bad. We don't want to divide by u. Are you not equal to 0? Then great, we're in business. That's a lot harder to check with a big matrix. So we need to know that the Jacobian is invertible. And this may not be easy to verify.
It may be invertible but close to singular as well.
It may be invertible but close to singular. So this may be it may be an invertible matrix, right? We've seen even for 2 by 2, we saw examples where it's invertible, but it's poorly conditioned, and this problem is going to magnify when you're working with huge systems. So Jacobian may be poorly conditioned. If it's not, we may sit down and prove Newton's method works, and then we go and do computations and see things blowing up because the errors are just building too quickly on us. So you want to handle on the condition number of this somehow, Jake.
When we're doing it in the single variable, we have to be close enough to the root, which I feel like it'd be easy to just move left or right, but it's going to be hard to figure out where to move.
Yeah, where's our initial guess? So you're right. When we were doing with a single variable, a scalar Newton's method, right? We needed a good enough initial guess. If we didn't have them, we might just say, oh, let's use bisection or something, right? And do a few iterations of that, and now we're close enough to go. That's harder here. There's no bisection method. There's no easy bisection method for nonlinear solvers. So this is actually a huge issue, is how do we come up with an initial guess? Okay, and there's no kind of easy method that works for every problem. Any others?
How good is that solver? Are we introducing errors?
How good is the linear solver? Yeah, we need to solve a linear solver, a system at each step, which could be expensive. And of course, if the matrix is ill-conditioned, then we might be introducing a lot of error. Yeah, Jake?
We need our Hessian to be continuous.
So the Hessian is a matrix, and for it to be continuous, we want all the components to be continuous. So that, it depends on your problem. That may be easier to check. It's easier to check than invertibility of a matrix. But you can weaken that condition a little bit and still have things work. But yeah, of course, just like with the scalar case, we kind of need things to be smooth enough. Any others? That's a pretty good list, actually. I think you guys basically hit every point on my list, so that's good. So what's the takeaway from this? It's not that solving nonlinear systems is impossible. Newton's method is great, and it's the foundation of a lot of nonlinear solvers out there, but you don't necessarily just pull it out of the box and use it. Maybe that's the takeaway here, is there's no one-size-fits-all method. So what you need to do is you need to also learn about your problem a little bit and say, is there extra structure to my problem that I could exploit? Maybe I know that my Jacobian is going to be sparse, have a lot of zeros, so I don't need to actually necessarily construct this whole Jacobian. I know ahead of time there's lots of zeros. I don't need to store all those zeros, right? And then there's linear solvers that specifically are good for sparse systems. That's common when you're solving PDEs with finite difference methods. You have sparse systems. You might learn about other structure of your system and you say, now I can use that to build a more efficient linear solver because I know my matrix has certain properties. In a lot of cases, they will do Jacobian-free type methods where instead of actually building this massive matrix, which is huge, you say, I just need a rule for how to take this matrix and multiply it by some vector. And that might be a lot easier to do. So there's lots of different variations that you can do. A lot of it builds on Newton's method, though. So this is a great method to know, to be aware of. There's tricks for how do you enlarge your region of convergence so that you don't need such a good initial guess. So there's lots of little tricks which you learn as you need them. But Newton's method is great, and it's just good to be aware of what's good about it and also what the limitations are. Are we happy with Newton's method? Nonlinear systems? Kind of, sort of. Okay, so that is basically all I want to do with root finding. So I'm going to jump on to chapter 3 then, which is function approximation. Okay, so the idea is we're given either a function or we're given samples of the function at some points, and we want to find a simpler function to approximate it. We've done some of this already this semester where we said, well, we need to compute cosine of 0.1 or something, but that's complicated, so I need a simpler representation like a Taylor series, a polynomial representation where I can evaluate it easily. Or I've got a whole bunch of data and I want to be able to interpolate the data, so I want to try to fit a polynomial to the data somehow and say, in between where I don't have data, I can still estimate what the function should be here. So we do function approximation all the time. So this is the basic problem. So we're given either a function okay, or we're given its values at a set of points. Okay, then our goal is to find a simpler function. I'll say polynomial for now, although there's certainly other things that we might try to use. So let's find a polynomial, p of x, okay, such that p of x is somehow approximately equal to f of x. All right, your first question hopefully is, how do I know such a polynomial exists even, right? before I go to a lot of work looking for it, maybe there's just none out there. Maybe there's no way to approximate this function by something simple. Okay, so let's try to answer that question first. And this is the Weierstrass approximation theorem. Okay, which says actually we can do this as long as f is continuous. Okay, so let's let f of x be continuous, okay, on some interval. I'm just going to say the interval is 0 to 1. It could be something else, and then you just have to kind of rescale things to put it on 0 to 1. But we're going to prove it works for x between 0 and 1. So this for 0 to 1, which again is not a limitation. Right, we do a change of variables in here if it's a different domain, and we can a continuous change of variables to shift our domain over to 0 to 1. Okay, and let's choose some error tolerance that we're willing to live with. So we call that epsilon. Okay, then this theorem says that there exists a polynomial, p of x, okay, such that wherever on this domain between 0 and 1 we choose to look, this function and this function never differ by more than epsilon. So such that f of x minus p of x is always less than epsilon, okay, for all x between 0 and 1. You look confused.
Is continuity really enough? Don't we need some sort of differentiability, I would think?
Is continuity really enough? Do we need differentiability? It turns out continuity will be enough for the existence.
Okay. So something like a sawtooth function or something can be approximated?
So even something like a sawtooth function, yeah, we can do. And in fact, I'm going to tell you a way to do it, because when we're going to prove this, we're going to actually do a constructive proof where we actually build the polynomial. Now, when I build the polynomial, I'm building some polynomial that accomplishes this. I'm not saying it's the optimal one or the one you'd actually want to use in practice. It might be that the degree of the polynomial is extremely high, much higher than you'd want to build, or there's simpler things that get the job done. But I'm going to build, just to prove this theorem, I'm going to build a polynomial that actually accomplishes this and doesn't require any derivatives of f. It will still hold at the endpoints, but not beyond the endpoints. And that's important to keep in mind. Interpolation is not the same as extrapolation, and extrapolation can get you into trouble very quickly. Okay, so let's do a constructive proof. Okay, so we're going to actually construct this thing. Okay, via what are called Bernstein polynomials. And again, I'm not claiming that in practice with real data this is what you want to use necessarily, but it will show us that this theorem works, and that we have a chance to go out and actually do something useful. So this is how we're going to define, okay, an nth degree Bernstein polynomial. Okay, it's going to make use of the function values of f, okay, at equally spaced points between 0 and 1, but no derivatives. Okay, so it's going to, here are the values of f that we're going to include. Okay, so these are the value of f at 0, 1 over n, 2 over n, 3 over n, and so on. So sampling equally. Okay, times this binomial coefficient, xk, and then 1 minus x to the n minus k. Okay, and what we want to show is that as long as n is big enough, this polynomial can stand in for this p here. Okay? Again, n may have to be very large to pull this off. So it's not necessarily something that you would want to actually build in practice, but it will get us the proof. Okay? So there are going to be a couple properties of this that we want to make use of. These follow basically from the binomial theorem. So what I'm going to do here is I'm not going to prove these properties right now. Again, they're relatively short proofs follow from the binomial theorem. What I have done is written them up and posted them on Canvas. So you can check that these properties hold. There's a limit to the amount of tedious calculations I want to do on the board for you. I'll make you suffer through, though. So the first thing is what happens if we're just using a constant function. Okay, if we're just using a constant function, things simplify down a little bit. Right, this f is basically not here. And this is a property that we should hope for if we're going to use this with interpolation. When we add this all up, it just simplifies to 1. Okay, and that's probably good. If I give you the simplest, dumbest function that I can possibly think of, which is a constant function, right, it makes sense that we should approximate it by a constant function, right, the simplest polynomial we can dream of. So this is reasonable. Again, it's not that hard to prove, and you can check on Canvas. Okay, then the other thing we want to check, there's a particular quadratic function that's going to involve these numbers here. So k equals 0 to n, k over n minus x squared. Okay, and then I repeat everything that's here. Okay, and this is x times 1 over x divided by n. Okay, again, it's not too hard to prove. I'm going to ask you to believe me for now, but you can go and check later. You don't just have to believe things that I tell you without proof indefinitely. All right, so let's try to prove this now. So let's start where we typically start, I guess. We'll start writing down things that we know. We know that f is continuous. Okay, so we can write down what that means. Right? That's what I always recommend when you're doing your proofs. Just go through what information am I given. Let's write it down and write down what it means. There's a definition of continuous, so let's write it down. Okay, so let's choose our epsilon. Right, epsilon, remember, was our error tolerance. Now, since f is continuous on a closed interval, what does that mean? You remember the definition of continuity? That's right. It's for all epsilon greater than 0. There exists a delta greater than 0, exactly, such that, yeah, so such that as long as I'm within a distance delta of x, my function is not going to wander away from f of x by more than epsilon. Okay, so it exists delta greater than 0. Okay, such that if x minus y is less than delta, then f of x minus f of y is less than epsilon. I'm going to put epsilon over 2 here. It doesn't really matter that much. If this is the kind of thing where the first time through you put epsilon, and then you go back and say, oh, it would look prettier if I put, at the end, if I put an epsilon over 2 at the beginning. It doesn't matter. It's purely an aesthetic choice. Okay, so f is continuous. That means this. It's continuous on a closed interval. That means it's bounded, right? Anything continuous on a closed set is always bounded. Okay, f is bounded. Okay, so we can define its maximum. Okay, so I've kind of written down the obvious information here. Then the next thing was there exists a polynomial. We've already thrown out a guess at that polynomial. So the obvious thing to do is start looking at this difference and see if we can get it to come out to epsilon. Okay, so let's look at the difference between my polynomial and my function. Okay, so my polynomial I can write down and then I need to subtract off f of x. Okay, leave yourself a little room to the right here. We're not quite done. I also need to be able to simplify things a little bit, right? If I just get to here, it's kind of not obvious how I would combine these terms or simplify them or anything. So we want to write f of x in a clever way that makes it easier for us to do this simplification. So you know things you're always allowed to do. You're always allowed to add 0 to things. You're always allowed to multiply by 1. That never changes anything. So what's a way I could manipulate this that doesn't change anything, but maybe makes it feel a little more like this guy?
Try to do an expansion on Taylor expansion on that?
So Taylor expansion is always a good guess. There's something else we can actually do here. And it's written on the board, actually. I can multiply by 1. There you go. You're pointing to 1 over here, Jose. This is 1. This is another name for 1. It's a funny way of writing 1. But it's a way that has a lot in common with this guy here, right? If I write 1 this way, all of a sudden I have terms that I can try to combine under one sum. And that's a good thing. Okay, so I'm going to multiply this by 1, written in a really very funny way. Okay, and I'm just going to remind you here that this is equal to 1. Okay, which means I can put this under one sum. I can factor out all the complicated looking terms that show up in both sums. And then I have a difference between f at 2 points. A difference between f at 2 points is good because we know something about the difference between f at 2 points. Okay, so all of this was equal to the sum. Okay, the difference between f times all this other stuff. Okay, again, this is good because I've got the difference between f at 2 points, and we've already wrote down something about the difference between f at 2 points, actually the absolute value of the difference. So what I want to do is get this in terms of the absolute value of this difference, and that I can do. Right? I can bound this by bringing the absolute value inside. Okay, all these terms out here are already non-negative. Okay, so let's try to get a handle on what's going on here. Try to bound it in terms of a sum that we can actually sum up easily, right? In other words, let's try to bound this in terms of things that involve either this sum or this sum, because these we know how to sum exactly, right? And it would be good to get this in terms of things we can sum exactly. Okay, so let's look at this difference. Let's just notice f of k over n minus f of x. We want to bound this. Now, under some situations, we can make this less than epsilon over 2, right? Certainly not for all values of k over n or all values of x, right? It only worked if they're close together. If x minus y are less than delta, then we can easily bound this sum. So I'm going to say this is less than epsilon over 2 if k over n minus x is less than delta. Otherwise, if I'm outside the realm where this is a valid estimate, what's kind of the best bound you can think of for this? M, almost, yeah. 2m, exactly. Right? So, I mean, this could be m, and this could be a minus m. So we could get 2m here, but we'll never get more than that. So why is it 2m instead of m? So it could be that the value of f here is equal to m, and the value of here is equal to minus m, right? So we could get them adding together. Okay, so we'll say if k over n minus x is greater than or equal to delta. This is good. This is small. This may not be small, so we better hope when we do this sum. Right? So if all I do is put a 2m here, and do the sum, then the sum of the rest is 1, right? So just bounding this by a 2m, I do the sum, I get 2m, and that's not small, right? We want this difference to be less than epsilon. 2m is not going to give us something less than epsilon. So we need to be a little bit more careful here. So what are we going to do instead? we're going to use the fact that k over n minus x is bigger than delta. And we're going to use the fact that this is the other thing that was easy to sum. This was easy to sum, but it's clearly not giving us what we want. But this is easy to sum. We don't know yet if it gives us what we want, but there's kind of a chance it does, right? Because if we could use this somehow, and we get something like this coming out, that'd kind of be good. N is in the denominator, and as long as n is big enough, we could make this small. We can make this less than epsilon, right? So this is good, but it means we need to bring in a k over n minus x somehow. So I need to play with this bound a little bit more. So this one's already small, so we kind of like it. This one, I would love to multiply by k over n minus x squared, because once I do that, this comes into my sum, and I can add it up exactly and get something small. So what I'd like to do is say this is the case. But of course, it might not be the case. Right? So right now, I've multiplied by something that is less than 1. And that doesn't make this inequality work. I need to multiply by something that's bigger than 1. So what do I know about k over n minus x here in this category?
It's bigger than delta.
It's bigger than delta, exactly. So I could change this a little bit and say, let's multiply by k over n minus x squared over delta squared. Now I've multiplied by something that's bigger than 1. Yep, see where this step is coming from? Okay, so I got bounds, right? And both bounds are going to give me something that I can add up easily and either get something that looks like epsilon or something that hopefully has an n in the denominator, and then I can let n be big. So let's go back to our estimate. So the thing we wanted to check was Bn f minus f. Now we know that this is less than or equal to all of this. Now I'm not quite sure for each particular value of x, which category I'm in. So I'm just going to do the worst case here. I'm going to say, what's the worst case in this category? What's the worst case in this category? And I'm going to add them up, and that will be a bound at least. So this is going to be less than or equal to epsilon over 2. Okay, and then I say, but that only works if this difference is small. So otherwise, I need to put in my 2m over delta squared k over n minus x squared times the rest of this polynomial. Okay, so now these are things, we've bounded this in terms of things that I can add up exactly, right? So I've just said, using these polynomials, let's find things that we can add up exactly, and I gave you a couple things that are easy to sum exactly. So if I do this, this is epsilon over 2 times something that summed to 1. And this was 2m over delta squared times something that summed to, what did I say it was? x1 minus x over n. Okay, so I got a bound on this, and now the big question is, can I make this less than epsilon, right? In order to finish the proof, I have to get a less than epsilon at the end of the day. So here I put this with a question mark. Can I make this less than epsilon?
Yes.
And the answer is yes, right? So epsilon was fixed at the beginning. Epsilon determined a delta, so delta is fixed, right? Delta had nothing to do with n. It was just dependent on the function. M is fixed. It just depends on the function. X is bounded by 1. 1 minus x is bounded by 1, right? So those are bounded. N is the thing I have freedom over, right? I can take as high degree a polynomial as I want to. So the answer is going to be yes, this works, right? As long as we take 2m over delta squared x, 1 minus x over n to be less than epsilon over 2. Right? Which holds as long as n is big enough. Okay, and that's the proof. That's what we wanted. We wanted to show that given NEF, right, which only had to be continuous, we've never used any derivative information about f, we could construct a polynomial such that the difference between f and the polynomial is always less than epsilon. Okay, so this proved the theorem. Okay, right, so it's a constructive proof. And again, I want to emphasize, I'm not suggesting that we actually use these Bernstein polynomials in practice for function approximation. You can do it, but what's the n that we need here? The n that we need here is actually quite large, right? If we rearrange things a bit, I've got a delta squared in the denominator, which is probably little, and I've got an epsilon multiplying it in the denominator, which is also little, right? So n could be very, very, very large. So this is just a proof that this works, this is possible. Then our task from here as numerical analysts is to say, okay, great, we have a task in hand that's possible. Now let's try to find a way to do it as efficiently as possible. Again, we'll build in structure of our original problem as much as possible. So what we're actually going to do in practice is not this. Okay, what we're actually going to do in practice, okay, is we start with a simple set of basis functions, whatever simple means. Okay, so we say these are functions that are easy to work with. Okay, they might be polynomials, and as you know, you can write polynomials in different forms, or you might be doing function approximation using trigonometric functions or something like that. So you can certainly imagine those too. And then we try to find a vector of coefficients. Okay. A0, A1, up to AN, so that f of x is approximately equal to a linear combination of these very simple basis functions. Right, so for example, I might choose this to be 1, x squared up to x to the n as a simple monomial basis, or you might think of something else. So that's where we're going to start going from here, is to think about, well, what kinds of basis functions should we use? How many of them do we need? How do we come up with these coefficients? Can we get error estimates when we do this? So these are the kind of questions we're going to start working on going forward from here. But I think I'm going to leave you there today.